In the previous lecture, we studied degenerate perturbation theory. That is, we learned how to use Rayleigh-Schrödinger perturbation theory in the situation where the unperturbed energy eigenvalue was degenerate, that is, corresponded to multiple independent eigenvectors. In this lecture, we are going to make use of that theory that we learned in the last lecture in studying a very particular system. The system is basically the sodium atom, or to be more precise, a 3p electron in the sodium atom. We are treating this under what is called the independent electron approximation. Remember, a multi-electron atom is more complicated than a hydrogen-like system simply because there are electron-electron repulsions. In the independent electron approximation, which works pretty well, especially for light atoms, we treat the effect on a single electron of all the other electrons in some averaged out manner. In particular, the outermost electrons in sodium effectively see a screening potential due to all the inner electrons, as well as, of course, the attracting potential due to the nucleus. So, one effect which this has is something which you all know. The 3s and the 3p levels of sodium are not of the same energy. 3s is lower, 3p is substantially higher. This is because the 3s electron spends a lot more time closer to the nucleus, that is inside the screening shell of the outer electrons, than does the 3p electron. In fact, this splitting between 3s and 3p energy levels is of utmost importance. After all, one of the most well-known features of sodium in physics, the fact that it emits a bright yellow light in a sodium vapor lamp, for example, is basically due to the transition between these 3p and 3s levels. Now, in addition to these, there is also a much smaller effect that's called the spin-orbit interaction. We have already talked about the spin-orbit interaction in hydrogen atom in the past. The spin-orbit interaction in sodium is similar. Its mathematical form is given by some function of r times the vector L dot vector S. So, this is a scalar operator L dot S times some arbitrary function of r, the radial distance. And we want to investigate the effect that this term has on the 3p as well as the 3s electrons. It's pretty easy to see that for 3s electrons, L being 0, this perturbation will have no effect, at least in the first order. So, we are looking at the effect of this perturbation on the 3p electron, or the 3p level of the sodium atom, and of course we are working in the independent electron approximation. Now, the 3p level in sodium is degenerate. It's actually 6-fold degenerate. So, there are 6 levels corresponding to ml values of +1, 0 and -1. This of course is because p corresponds to L equal to 1, as well as ms equal to ±12. And these are the forms of the corresponding wave functions, where R31R is a radial wave function that you get by solving the rather complicated problem of the electron in the Coulomb plus the screening potential. The y1 ml function of theta phi is our familiar spherical harmonics for L equal to 1, and chi ms are the spin eigenfunctions, which of course correspond to the 2 possible spin eigenvalues, ms eigenvalues. So, these are 6 degenerate levels, and from the general theory of degenerate perturbation theory, we know that in order to find out the energy corrections to first order, we have to diagonalize a 6 by 6 matrix. Which 6 by 6 matrix is this? Well, in order to figure that out, we need some basic results, which is what do L plus, L minus and L0 due to, after all, what L0 does to YLM is pretty simple. It just gives you ML H bar times YLM. What L plus does to these states and what L minus does to these three states are also pretty straightforward. You already know that from the theory of angular momentum. L plus acting on the highest ML state, ML equal to plus 1 here, kills it, so you get 0. L plus Y acting on Y10 gives you a Y11. The factor root 2 H bar is something which we already know. We have already studied that earlier, but this is really root over J minus M into J plus M plus 1 H bar. And similarly, L minus lowers Y11 to Y10, lowers Y10 to Y1 minus 1, and of course kills Y1 minus 1. In addition to these, we will need the results at S plus acting on chi plus, of course 0. You can't raise a spin up any further. S plus acting on chi minus is just 1 H bar times chi plus. So factor of 1 of course comes from the fact that root over J minus M into J plus M plus 1 for J equal to half, M equal to minus half is actually exactly equal to 1. And similarly you have S minus chi plus equals H plus H cross chi minus, S minus chi minus is 0. Now why do we need these results? Because we can easily write down L dot S in this form. This is pretty straightforward to do and we have already done this before. That L dot S can be written down as half L plus S minus plus half L minus S plus LZ SZ. So what is the perturbation term, or what does L dot S do to any particular of our degenerate eigenfunctions? Let's just take Psi31 minus 1 as an example. Psi31 minus 1 is of course made out of R31, which is a function of R, and none of these operators, the angular momentum operators, care about the radial part or radial coordinate, so R31 can simply go out. Then you have this operator which is of course L dot S acting on this combination. This is ML equals 1, so Y1 ML equals 1 and MS equal to minus half, so chi minus. Now it's pretty easy to figure out what this is going to be. You just need to apply these three terms separately. The first term, of course, L plus acting on Y11 kills the first term. In fact, S minus acting on chi minus would also kill the first term. So you get 0. The second term, L minus acts on this to give you Y10 with a root 2 H bar. And S plus acts on this to give you an extra H bar. So H bar, chi plus. So this is what you get. Similarly, LZ, SZ is pretty straightforward. LZ gives you just 1 H bar and SZ gives you minus H bar by 2. Putting all these together, apart from a factor of H cross square by 2, which is there in both the terms, you get root 2 H bar, Psi31, that's common, ML0, MS plus, so Psi31 0 plus, and here you get Psi31 1, and this is a typo, this has to be chi minus, so Psi31 1 minus. So this is just an example, but you can easily apply L dot S on all the 6 terms and you can figure out what their effects are going to be. This is pretty straightforward. Of course, you should do it yourself. Now, this allows us to easily write down the matrix element for the perturbation. Apart from the H cross square by 2, these are the factors inside the matrix here are straightforward to find out from these expressions. The only factor that is not obvious from here is the factor A in front, which of course is nothing but the radial part, which comes from taking the R31R, which is the same for all the Psi31s. So you get R31 square here times FR and you integrate that. This gives you the radial integral, whatever that is sits here. Now we have to diagonalize this 6 by 6 matrix. Although diagonalizing a 6 by 6 matrix is usually not quite an easy task, here the task is much easier because, as you can see from the structure, you basically have a 1 by 1 matrix sitting here, another 2 by 2 sitting here, another 2 by 2 sitting here, another 1 by 1 sitting here. Effectively, the job of diagonalizing the 6 by 6 matrix boils down to diagonalizing two 1 by 1 matrices, which is trivial absolutely, and two 2 by 2 matrices, which is not trivial, but which is simple enough. So the eigenvalues can be calculated very, very simply. Once again, I leave this to you, but this is something you can almost do in your heads, despite being a 6 by 6 matrix. And it so turns out that you get 4 of these eigenvalues, which are equal h cross square by 2 times A, and 2 other eigenvalues which are equal to each other, which is minus 2 times h cross square by 2A into A. So these eigenvalues, of course, are the first order energy shifts. These are the energy shifts due to the perturbation on levels which were initially degenerate. Of course, the corresponding eigenvectors can also be found out very easily. In fact, the first and the last one are things you can just find out by inspection. The other 4 take slightly more work. Remember, this is effectively working with 2 by 2 matrices only. And this means that if you take these 4 coefficients marked in red, you end up with this set of eigenvectors. This one, of course, is just psi 311 plus. This one corresponds to psi 311 minus with a factor of 1, and psi 310 plus with a factor of root 2. The root 3 here is just for normalization. This one similarly is root 2 times psi 310 minus, and this one is plus 1 times psi 31 minus 1 plus. Again, root 3 for normalization, and so on. So these 4 states stay degenerate even after the perturbation is applied. So at 6 degenerate levels, applying the perturbation splits the degeneracy a bit. So instead of 6 levels which are the same energy, now you have these 4 levels which are the same energy, namely whatever the unperturbed energy was, plus h cross square by 2 into A, and 2 other levels, these ones which come from with the blue eigenvectors here corresponding to the blue eigenvalues. These 2 correspond to the unperturbed energy minus 2 h cross square by 2A, at least to the first order in perturbation. So these are still degenerate to first order in perturbation theory. And this is the result that you get from first order perturbation theory. Now, we saw that in the last example, despite the fact that we had to work out a 6 by 6 diagonalization problem, it turned out to be not that difficult because the matrix split into nice blocks. Now, you can actually get an even better result if you are lucky or if you are clever. Remember, what we need to do is diagonalize a d by t matrix if the unperturbed energy level is d-fold degenerate. Of course, this matrix depends on which set of d independent functions do we take to be the basis functions or the unperturbed eigenfunctions to start with. So the matrix depends on the choice of the basis functions. If we are lucky, as we were in the last case, we end up with a simple matrix, and our job is considerably less. Well, a bit of thought may help matters. You should not really leave this entirely to luck. And for this, you have to realize that the basis vectors that we choose are often chosen as simultaneous eigenvectors, not only of the Hamiltonian, but of the Hamiltonian with another set of operators, observables, Hermitian operators, which commute with the Hamiltonian and with each other. So basically, this is a matter of labeling. You keep on adding more and more commuting observable to your set so that the eigenvalues of all of these ultimately completely identify which state you're dealing with. Now, then 2 different basis vectors in the set of course differ in the eigenvalue of at least one of these operators. That is what we mean when we say that the set of commuting observables is complete. Now, this is a basic result. If psi 1 and psi 2 are eigenvectors of operator A with different eigenvalues and A commutes with V, then it is very easy to see that psi 1, psi 2 matrix element of V has to be 0. All you have to do to establish this is take the psi1, psi2 matrix element of this commutator, which has to be 0 of course, and then use the fact that psi1 and psi2 are eigenfunctions, eigenvectors of A with different eigenvalues. You have already done this before, so it should be pretty easy for you to work out. Now we are going to exploit this result. If we can find the CSCO, or complete set of commuting observables, such that the perturbation commutes with quote unquote all the operators in the CSCO, then this matrix that we have to diagonalize will have non-zero elements everywhere outside the diagonal, which means it will start out being diagonal. Of course, here all is within quotes, because you have to realize that one of the operators in the CSCO is the Hamiltonian, and our perturbation presumably does not commute with that. If it did, then our entire job would have been much simpler. Now, this fact that if you could choose a CSCO, choose the basis functions to be simultaneous eigenfunctions of a CSCO, where all the operators, apart from the Hamiltonian that is, commute with the perturbation, then the matrix that you have to diagonalize starts out being diagonal, makes your life a lot simpler. If you can find such a CSCO, that is. Now, for our case, remember that we had a purely spherically symmetrical Hamiltonian to start with. This, by the way, is the Hamiltonian not of the actual sodium atom, but the Hamiltonian of the sodium atom in the independent electron approximation for the valency electrons. For inner electrons, the electron-electron interaction, even the effective electron-electron interaction, is not spherically symmetrical. But for the outer electron, the inner shells being completely filled, the net effect on the outer electron is effectively to produce a spherically symmetrical screening potential. Now, for such a spherically symmetrical Hamiltonian, this has to be rotationally invariant, which means the operators which generate spatial rotations, namely L1, L2, L3 or Lx, Ly, Lz, must commute with the Hamiltonian. Of course, this Hamiltonian is purely spatial, so it doesn't have anything to do with spin, so it obviously commutes with spin. These are operators which act on different vector spaces, so they commute trivially. The reason why, of course, we are talking about all this is that our independent electron approximation Hamiltonian for the alkali atoms and for the sodium atom in particular, as long as we don't take into account the L dot S terms, this is a purely spatial spherically symmetrical Hamiltonian and commutes with L and S. Since the Hamiltonian commutes with L and S, then a possible complete set of commuting observables that we could use is the Hamiltonian. Along with that, we take L square, Lz, S square, Sz. Of course, remember the operators in the CSCO must commute with the Hamiltonian in this case, but also must commute with them between themselves. That's why L square, Lz, S square, Sz is a good choice. The corresponding eigenstates are exactly what we have been talking about so far. These are the psi, NL, ML, MS eigenstates. Of course, there are 5 operators here, and you have only 4 labels corresponding to the 4 eigenvalues. That's because the S square eigenfunction or S square eigenvalue is always half into half plus 1 h cross square, so it's never explicitly mentioned. Now, there is also another possible CSCO, something we have learned when we talked about rotations. The reason why the other CSCO will be important is that L dot S perturbation is not diagonal in this basis. So L dot S does not commute with all the operators in here. In particular, does not commute with Lz and Sz. But the other possible CSCO is made out of Hamiltonian, L square, S square, J square and Jz, where J is of course L vector plus S vector, the total angular momentum vector, and we had already seen earlier that this forms a complete set of commuting observables. and L dot S commutes with each one of L square, S square, J square, Jz, not with the Hamiltonian H, but that's not what we need. So the perturbation is already diagonal in the basis formed by the eigenvectors of these operators, namely psi n L j m j. Once again, should have been psi n ls j m j, but s is something you don't mention because it always is half. Since the perturbation is already diagonal in this basis, if you use this basis to find out the first order energy corrections, the calculation becomes trivial. All you have to do is, instead of figuring out the entire d by d matrix, you just have to find out the diagonal elements, and there is no further calculation to be done after that. The diagonalization is already complete. So the diagonal elements, as I said, are the eigenvalues, and they are the first order corrections. Now to figure out what they are, well, all you have to do is use this result. L dot S is half J square minus L square minus S square. We derived this when we were talking about angular momentum operators. But this of course looks very much like the standard class 11 result for addition of vectors. And the first order energy correction due to this term will be given by simply delta Ej will depend on J, first order, A times whatever this expectation value is. Well, this is actually L dot S expectation value here, which is where I have replaced L dot S by this combination, and the f of r times r31 whole square integral, that's of course in the A. And you can immediately see that this result, since the states psi and Lj, Mj are actually eigenstates of J square, L square and S square, it's trivial to calculate this result, and this is what you get. And if you put in L equal to 1 and S equal to half, you can easily see that there will be two cases, J equals 3 by 2, and for which, if you just use this formula, you will get an energy shift of h cross square by 2 into A. Simply putting in 3 by 2 for J, so 3 by 2 into 5 by 2 minus 1 into 2 minus half into 3 halves. On the other hand, if you put in J equal to half, this changes to half into 3 by 2, the calculation goes in the very same manner, and you end up with minus 2h cross square by 2a. So these are the two energy shifts, remember, that we figured out by direct calculation a while ago. But if we were to switch over to the psi n L j m j basis, this would be trivial to work out. The eigenvectors that we had found out earlier, remember we had started out with the psi n L ml ms vectors, did not get a diagonal matrix, but found a 6 by 6 matrix which was pretty easy to diagonalize, diagonalized it, and found out a set of 4 and 2 eigenvectors corresponding to splits which are the same respectively. And those eigenvectors, if you look carefully, are nothing but the corresponding psi n L j m j eigenvectors. In fact, J equals 3 by 2, of course, has 4 vectors corresponding to it, mj going from minus 3 by 2, minus half, plus half, and plus 3 by 2, and J equals half has 2. And if you remember your Clebsch-Gordon theory, you can figure out that these are exactly those eigenfunctions. So the work which we did earlier could have been circumvented if you had just gone on to the right choice of basis at the very beginning. So let's now go over to a slightly more complicated situation. This situation is physically the same physical system, but now we have turned on or switched on a magnetic field. So we are considering a sodium atom in a magnetic field. So we have this. Well, before we go there, let me talk a bit about the physical consequence of the degenerate perturbation theory result that we have found. Remember, the bright yellow light of sodium is produced by a transition between the excited 3p electron and the ground state 3s electron. The fact that this produces a bright light in the visible region is because of the fact that the 3p and 3s levels are shifted sufficiently from each other because of the screening effect that we have already discussed. But now, what happens due to this L dot S interaction term is a very small but highly noticeable effect. Because of this L dot S term, the 3s level doesn't split, but 3p, the 6 levels in 3p, 6 orbitals, split into 2 sets, 4 orbitals with one energy, 2 with another energy. So transition between 3p and 3s levels is really not between 2 fixed energy levels, one for the 3p and one for the 3s. It's actually between 2 for the 3p and 1 for the 3s, which is why you get 2 different wavelengths of light being emitted, very similar wavelengths, because the energy gap, the splitting in 3p is small, but that small splitting is enough to produce the famous sodium doublet. The fact that the bright light in sodium is not really a single wavelength but 2 very close wavelengths is because of this L dot S splitting. Now, if I put the same atom in a magnetic field, how do things change? Now, when I put this in a magnetic field, what happens is that you have a Hamiltonian, which is H0, which is the independent electron approximation effective theory Hamiltonian, which is spherically symmetrical for the outermost electron, not the Coulomb problem, but Coulomb plus screen potential, plus of course this thing that we have been talking about, the spin orbit interaction term, plus another term which is basically proportional to the magnetic field, and it depends. I am assuming that the magnetic field has been taken in the z direction, so this is really B dot L, so that's BLZ times a constant called the Bohr magneton. You would expect a mu b b into B dot S as well, but it so turns out that the spin produces twice as big a magnetic moment than does angular momentum, unit by unit. So that is the source for this factor 2 here. The real reason why there is a 2 here is relativistic, and when we study relativistic quantum theory, we should be able to see where this term comes from. So as we have already said, H0 is spherically symmetrical for the outer electron, but the unperturbed, so that means the unperturbed energy levels, unlike for hydrogen where the unperturbed energy levels depend only on n, which is why you get a 2n square order degeneracy, all L values, all ML values corresponding to the L values, all that double of that because of the spin, all of them are degenerate. That's for the Kepler problem, of course. We have already seen that the spin orbit interaction, the Darwin term and the relativistic correction term shifts that slightly and gives rise to fine structure in hydrogen spectra. In sodium, because of the screening effect of the inner electrons, the 3s and 3p, as we have already said, are not degenerate to each other. There's a substantial energy difference. So the unperturbed energy levels correspond not only to a fixed value of n, but a fixed value of n and L. And such a state is 2L plus 1 fold degenerate from the 2L plus 1 ML values possible, twice that, because each one corresponds to 2 possible spins. So you have 2 into 2L plus 1 fold degenerate unperturbed energy levels. But on top of this, you have 2 perturbations, not just one, this one and this one. And because of this degeneracy, we actually have infinitely many possible choices for basis states. I am going to take 2 into 12 plus 1 basis states no matter which way I do it, but the precise ones I choose, there are infinitely many choices there, but there are 2 obvious choices. One of them is the Chi NL MLMS and the other is the Chi NLJ MJ. As we already saw a while ago, if the L dot S interaction is all we have to worry about, then the better choice would be Chi NLJ MJ, because the perturbation would be diagonal in that basis immediate, which also tells you that the unperturbed energy levels, the 0th order energy levels, will be better thought of as Chi NLJ MJ. Now here we have two perturbation terms, of course, the HSO and HZ. And the way we proceed will have to depend on which one is stronger. If they are both of the same order of strength, then things become very, very complicated. But things are much simpler when one of these perturbation terms is much stronger than the other. And notice that Hz, the Zeeman term, the term which is due to the magnetic field, is proportional to B. So the relative strengths of these two terms can be controlled from the outside by changing B. If we are dealing with a very strong magnetic field, in fact for most systems this has to be really, really strong magnetic field, unusually strong, then the Hz term, the so-called Zeeman term, dominates over the spin orbit term. So this is the perturbation we are going to apply first. So we treat its effect first on the degenerate eigenstates of H0, and if this is the perturbation we are going to treat, then of course we should choose an eigenbasis, if possible, which are already eigenstates of these operators, which means we want to choose an eigenbasis coming from a CSCO where apart from the H, everything else commutes with Lz and Sz, and we already have such an eigenbasis. These are the Chi NL ML MS terms. Remember, L square, S square, Lz, Sz are the operators which gives rise to this particular eigenbasis, and these operators of course commute with Lz and Sz. And if you want to calculate the first order energy correction, you do not have to go through this whole machinery of degenerate perturbation theory. All you have to do is take the expectation values, because you know that they are going to be your first order energy corrections. And these expectation values are trivial to calculate. Lz gives rise to MLH bar, Sz gives twice MSH bar, and okay, I missed out of H bar factor here, but this is apart from an H bar factor, this is essentially what you will get. Now, the kind of spectrum this gives rise to turns out to be a situation where if you had a single line when there was no magnetic field, what the magnetic field does is that it splits it into three lines. Now, why three in particular? Why not more? That depends on the fact that these levels are split, but they are split equally for both 3p and 3s. The details are going to be left as an exercise, but once you take the selection rules into account, and once you take the fact that the levels are split equally because of the magnetic field, it turns out that you will get only three distinct. This, by the way, is also exactly what Zeeman predicted from his classical approach to this problem. This is why this is called the normal Zeeman effect. It so turns, I am writing this normal in quotes simply because it turns out that this normal is actually rather unusual. The name is pretty misleading because the normal Zeeman effect is not normal at all. At least it's not the usual case. Of course, you have the perturbation HSO still on top of this, but since we have assumed that HSO is much smaller than Hz because of the large size of the B, the effect of the spin orbit interaction can be treated as a perturbation on top of this. Of course, now you no longer have a degenerate theory. These are your energy eigen functions, so you have to use the Chi NL ML MS basis. You don't have a choice now any longer. And when you use these and non-degenerate perturbation theory, the first order energy correction due to the spin orbit term is also pretty easy to take into account. Okay. So this is a strong magnetic field effect, also sometimes called the normal Zeeman effect. What happens in a weak magnetic field? Well, here the HSO term, the spin orbit term, dominates over Hz. So that's the perturbation you have to take into account first. We have to treat it first. Since HSO is diagonal in this particular basis, as we have already seen a while ago, the first order energy correction due to this spin orbit term has to be calculated using this basis. We have already calculated this before, so I am not going to go through this calculation again. This is nothing new. This is what we did a while ago when we were dealing with the spin orbit perturbation. But what is important here is that at the end of the day, this gives rise to a splitting of the degeneracy that we had, and unperturbed levels now are psi n L j m j. So, and the splitting due to the magnetic field, the Hz term, even though it is smaller than the splitting due to HSO now, is still the really important thing here, because the physical phenomenon that we are investigating here is what happens to spectral lines when you switch on the magnetic field. The splitting due to the magnetic field has to be calculated using the operator mu b Lz plus 2Sz, but you have to take its expectation value in the psi n L j m j terms. Remember, the spin orbit interaction has already made the choice or forced the choice of the unperturbed levels on us. And so this is the calculation we have to do. And of course here these operators depend only on L and S. So the radial part plays no role. You end up with mu b, the matrix element, the expectation value of Lz plus 2Sz in this basis state. Now we had learned how to calculate such matrix elements in the last series of lectures on rotations in quantum mechanics. In particular, we had learned that to calculate the matrix element between two angular momentum eigenstates of any component of vector operator, you can use the projection theorem, which is essentially you can replace the vector by its projection in the direction of the j vector, and you end up with calculating the corresponding matrix element. Expectation value is what we need here, but in general corresponding matrix element for the corresponding j component. So for us, this is really simple. You just take the L vector plus 2S vector, whose z component you were talking about. You take its projection in the j direction, L plus 2S dot j into jz by j square expression value, which is j into j plus 1 h cross square, and you're done. Now this calculation is pretty straightforward. You can calculate it using this. After all, L plus 2S dot j is simplified by the fact that j plus s dot j, and j plus s is j dot j is j square, and s dot j is of course this. And making use of this, we can finally write down delta Ez1, the first order correction, is going to be mu bb times an h bar times m coming from here. So mu bb m h bar times a factor of the order of 1, which comes from this. This factor is rather famous. It is called the Landé-G factor. Now I will leave the calculation of the Landé-G factor as an exercise for you. What is very important about this is that this G factor depends not only on L and S, it also depends on J, which means that for the same L value and S value, S of course is always half, the two different J values that you get, L plus half and L minus half, they split differently, which means that you end up with many more lines than you would have if the splitting had been exactly equal. If the splitting had been equal, many of these lines, permitted lines, would end up having the same wavelength. However, here some of these lines, because of the differential splitting between different J values, will end up giving rise to more lines than just the 3 that we had for normal Zeeman effect. So this actually was the observation when people could build good enough spectrometers to resolve the lines when you subject an alkali atom to a magnetic field, resolve with spectral lines. This was not in accordance with the classical theory of Zeeman, so this was called the anomalous Zeeman effect to begin with. As I explained, the anomalous Zeeman effect should have been called the normal Zeeman effect, because that is what happens most of the time. The extremely strong magnetic fields for which you will get the same number of lines that classical Zeeman theory predicts is actually very, very unusual. You can hardly ever find laboratory setups where such strong magnetic fields can be produced. There's another case when you do get small number of lines. That's when the transition is to a S level, S orbital. The reason for that is pretty straightforward. I will let you figure it out yourself. Anyway, working out how much these splittings are, exactly how many lines you get, why you get different lines, these will be left as an exercise in a coming assignment. However, it should be pretty easy for you to work it out yourself. So, what we have done here is illustrate the fact that degenerate perturbation theory, though complicated relatively compared to non-degenerate perturbation theory, can be simplified a lot if you make a proper choice of basis, and this proper choice of basis is essentially what makes the Zeeman effect behave very differently in the case where you have a weak magnetic field or a strong magnetic field.